by physical experiments at first, and second by mathematical equations or mathematical formulas, or by making two-dimensional simulations of space-time. So if we define something like this as a fabric of space-time, which in classical physics we consider and we think that space is flat, so all lines on space are flat. This is the result of classical mechanics or classical physics. But in general theory of relativity, we don't say such things. So matter tells space-time how to bend, and space-time returns the compliment by telling matter how to move. So if you have a massive object somewhere in the universe which has to be in the space-time, you have a curvature in the space-time. And this curvature tells other objects in the universe, close or far from this object, how they move in the universe. So, if there is an object with a mass m, it makes something like this in a space-time fabric. So, if there is another object coming close to the mass m, for example like this, he has to obey the form of space-time for the motion that it wants to take. Since Aristotle to Einstein, we don't want to talk about the first two ones because we know them. They're classical, defined as classical physics. But in general theory of relativity, all kinds of motions are unified, including accelerated motion. Gravity and acceleration are unified and depend on the observer. This is very important explanation. Depend on the observer. We will see in the future. Space-time is not a fixed background anymore. Space-time and matter interact with each other and affect each other. So if we want to describe the curvature of space-time and the effect of the mass and energy on the space-time, Einstein proposed this equation. G, which is the curvature of space-time, equals APT. And T is both mass and energy density, because mass and energy are not two different quantities. They're always the same. So you can, when you hear energy, you can imagine the mass, and when you hear mass, you can imagine the energy. So if